Thank you for the introduction. My name is Chuck Wilkinson, and today we will be discussing thermal leak test applications and related solutions. We will be reviewing the different reasons for leak testing, establishing leak rate specifications, defining leak test technologies, reviewing typical automotive thermal applications, and talking about a patent-pending IHX, or internal heat exchanger, air conditioning hose case study. Vacuum Instruments Corporation, established over 60 years ago, is one of the world's largest companies devoted solely to the research, design, manufacture, distribution, and service of leak detectors and complete leak detection solutions. VIC is the only company in North America to offer both organically manufactured instruments and custom systems for tracer gas and air leak testing. In addition, we offer a variety of tracer gas management products, including helium recovery and evacuation and backfill instruments. VIC's staff of engineers, system design personnel, and application specialists constitute the most experienced body of leak detection experts in the world. Vacuum Instruments Corporation offers an unparalleled breadth of applications knowledge and gas handling experience, along with the fastest, simplest, and most robust leak detectors in the industry. Billions of products have been tested with VIC's complete turnkey leak detection solutions, portable mass spectrometer helium sniffers, general-purpose helium leak detectors, as well as mass flow and pressure decay air-based systems. The first issue to come to grips with is that everything leaks to some degree. As an extreme example, VIC has supplied equipment that tests for a leakage that is equivalent to one bubble in a few thousand years. One wouldn't want to wait that long for a bubble to form. So it's important that the leak rate specification be appropriate for the type of product and its design criteria. Once that has been determined, we can tackle the question of how to test and quantify the product's leak rate. Each manufacturer will have reasons to perform leak testing operations. Obviously, quality is an important issue. Reducing warranty costs to replace defective components that have already been installed into automotive vehicles is a major reason, as could be product performance. Take, for example, an air conditioning system where fractions of an ounce loss of refrigerant would result in a significant loss of cooling efficiency. Or the product may contain hazardous or toxic gas, as is the case for commercial or residential gas meters and its associated regulation and valving. In this case, there are both safety and economic issues of concern. Let's first understand the nomenclature behind the leak rate specification. Leak rates must always be expressed in terms of volume of gas or liquid specified over a unit of time and at a given pressure and temperature. There are many examples of this, including ounces or grams per year of refrigerant, cubic centimeters per minute, or SCCM, or perhaps the most common unit in the industry, atmospheric cc's per second. Helium is by far the most popular tracer gas used in today's leak testing arena. The gas was first used for leak detection during the Manhattan Project as a means of verifying vacuum process. Today, helium is used to test the leak integrity for many products in both commercial and consumer industries. The reasons why become obvious when you consider the following. It's one of only a few noble gases. These elements are totally inert and non-toxic. Its concentration in our environment is very low, at approximately 5 ppm, or parts per million. And finally, it can be easily resolved from the other elements using a mass spectrometer instrument. So now that we have an understanding of the units of measurement, let's take the next step to determine the type of technology that could be employed. The chart here shows the various technologies as they relate to relative sensitivity or leak rate. As you move down through the technology column, you will note that the mass spectrometer vacuum testing method provides the broadest range of leak detection, from 1 cc per second to 10 to the minus 12 cc's per second, which, by the way, is 11 zeros followed by a 1. Let's hone in on one particular market application, that of thermal products. In this slide, we have defined the various thermal products on the left-hand side of the chart and the various VIC product offerings on the right. Each VIC solution has been optimized to match the sensitivity level required while always providing the highest level of value. The next few slides will offer an explanation of the features benefits for the various testing approaches. As the name implies, helium accumulation involves placing the object under test in a hermetic enclosure, or what is sometimes referred to as a clamshell. The object is then evacuated and backfilled with helium to a preset pressure. After a period of time, the chamber or clamshell is sampled using a helium sniffer to detect the presence of any helium tracer gas that has leaked out during the accumulation phase of the test. The time required to accumulate is dependent upon the leak rate specification of the object and the free internal volume of the chamber or clamshell. Generally, this approach is applicable to those applications with relatively large leak rates or whose internal volume for the fixturing can be kept to a minimum. Hard vacuum testing, by far the most sensitive and accurate leak testing method. Here, the object under test is placed into a vacuum-suitable chamber. As stated previously, the object will be evacuated and backfilled with helium gas to a preset pressure. The chamber will also be evacuated to a level on the order of 50 to 200 microns. Once the vacuum level in the chamber has been achieved, the leak detector will sample the environment of the chamber. The advantage of sampling under vacuum is a much higher degree of sensitivity, as well as an enhanced signal-to-noise ratio, providing the highest level of repeatability. Sniff testing. Here, the leak detector is fitted with a probe that allows the mass spectrometer to sample at atmospheric pressure. In practice, as was the case in the two previous examples, the object under test is first evacuated and backfilled with helium to a preset pressure. The probe is then scanned over the object. The distance from the object should be kept constant, as well as the scan speed. In application, it is good practice to limit the scan speed to 1 to 2 inches per second, while maintaining a probe distance to workpiece of 1/10 to 1/4 of an inch. Getting back to the thermal applications, here's examples of automotive front-end applications. The typical leak rate specification and the type of recommended testing methodology round out this slide. You will notice that within the group of products, there is over a 1 million times difference in sensitivity requirements, from 10 to the minus 1 cc second to 10 to the minus 8 cc's per second. Hence the advantage of having one technology to cover a myriad of related applications. The engine cooling components, which usually contain a liquid media, have a less sensitive requirement, or in other words, a larger leak rate allowance. These products generally have their specifications expressed in cc's per minute, rather than the conventional cc per second. The graphic here depicts the typical components in the engine cooling system. As example, the radiator has a leak rate specification of 4 to 5 SCCM, or cc's per minute, and typically is tested in an accumulation leak test system using helium as a tracer gas. Rubber hoses and the plastic expansion tanks are usually tested from a few cc's per minute up to 50 cc's per minute, primarily using air leak testing methods or perhaps handheld tracer gas sniffing. Finally, heater cores typically have a leak rate specification of 0.5 to 1 SCCM and are tested with either a hard vacuum or accumulation system depending upon the required production rate. As shown, the automotive air conditioning assembly also has many components requiring leak detection. As these components contain a refrigerant gas at relatively high pressure, their corresponding leak rates are more stringent than in the previous examples for the engine cooling components. Condensers, evaporators, and AC hoses all have leak rate specifications in the 10 to the minus 5 to 10 to the minus 6 cc per second range, or 0.1 ounce of refrigerant per year. The compressor, due to the nature of its dynamic shaft seal, is generally tested to a slightly larger leak rate specification. In either case, these parts are typically tested using a hard vacuum leak test system with helium as the tracer gas. The expansion valve has a much tighter leak rate specification, typically on the order of 10 to the minus 8 cc per second, and would require a hard vacuum leak test system. While internal heat exchangers, or IHX as is commonly called, techniques have been long utilized in traditional refrigeration systems, Recent improvements to automotive AC hose design have resulted in the implementation of IHX hoses in automobile air conditioning systems. The automotive industry goal in using IHX resulted in increased fuel economy and reduced emission levels. But if leaks in the IHX system exist, then this efficiency is not realized. IHX components offer leak detection manufacturers higher technical challenges not realized in standard thermal leak testing applications because of their coaxial section design. The presented case study will demonstrate this point. Our customer, who is a leading supplier of automotive AC hose assemblies, was performing the accumulation method of leak detection. But this method could not ensure the leak integrity of the inner tube in the coaxial hose assembly and test to the leak rate specification. So the customer turned to VIC to solve the application problem. We developed a hard vacuum leak test system that not only tests the inner and outer tubes separately, but also measures the leak integrity of the entire assembly in one test. VIC's patent-pending test methodology was implemented in the Scepter, which is VIC's hard vacuum system for thermal applications. The Scepter allows the parts to be loaded into the fixture assembly, which is in the chamber, and evacuates and charges first one circuit of the IHX part independent of the second circuit while performing a leak test. Then isolates and performs a test on the second circuit, thus allowing us to completely test the leak integrity of the entire coaxial section in one complete testing sequence without ever having to remove the part from the vacuum chamber. The Scepter is a complete hard vacuum test system that is specifically designed for thermal leak detection applications. The Scepter utilizes standard components like the chamber and frame, VIC's MD490M industrial leak detector, chamber evacuation pump package, gas handling cabinets, electrical package including controls and operator interface, and a chamber-mounted calibrated gas leak, all packaged together, offering a leak detection solution to meet the most demanding thermal application testing needs. Custom tooling is supplied with the Scepter that links your product to the system. The tooling features ergonomic designs that allow interchangeability between the pallets for speed and ease of product tooling changeovers. VIC offers a complimentary installed base audit to all customers as well as our potential customers who have sizable installed base of leak detection equipment. This audit can encompass custom leak detection equipment as well as leak detectors themselves. We offer to not only audit your own equipment in your installed base, but all the leak detection equipment that you currently own. During the audit, we will also evaluate feasibility and the return on investment if a helium recovery system were to be implemented. So, in summary, customers should ask themselves the following questions. What is the maximum allowable leak rate? Will 100% leak test be necessary, or will an audit or statistical testing program accomplish the same goal? Will failed parts be scrapped or repaired? Is it necessary to know the size and location of the individual leak? Where is the optimum point in the manufacturing cycle to perform the leak test? What are the consequences of a loose specification or one that is too stringent? What is the best method in terms of performance, compliance, cost, and available resources? And finally, will manual test procedures suffice, or should automation be considered? If you are in the Michigan area during the week of October 22nd, please stop by our booth at the Automotive Testing Expo to see some product demonstrations and talk in detail to our application experts. Thank you for your time, and we will open up the discussion for any questions.